Hello everyone. In this video, we are going to talk about intersection of sets from the chapter Sets Class 11 Max. So you see, the intersection of two sets A and B, it is a set of all elements which are common to both A and B. So intersection of two sets is actually defined as it is a set of all elements which are common to both the sets A and B. You see, this symbol, this is a kind of inverted U. This symbol is actually used to denote the intersection. We usually write the intersection as A intersection B is equal to set of all x such that x belongs to A and x belongs to B. That is, while we are taking the intersection of two sets, we will be getting a new set, and in the new set, we will be having the elements which are present in both the sets A and B. Okay, for example, let A is equal to set of 2, 4, 6, 8 and let B is equal to set of 6, 8, 10, 12. So here, if we find out A intersection B, we can write it as, you see, we have to consider the common elements present in both the sets. So you see, when we consider 2 is present only in A, not in B. So we cannot write 2 here. When we take 4, it is present only in A, not in B. So we cannot write it here. So when you consider 6, it is present in both A and B. So you can write 6 here. Similarly, when you consider 8, it is present in both A and B. So you can write it here. Now here in B we have 10 which is not in A, 12 which is not in A. So you cannot consider this 10 and 12 here. So A intersection B will be equal to set of 6, 8. Okay. Now let us consider another example. A is equal to set of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and B is set of 2, 3, 5, 7. So here you can see that the set B, you see all the elements in B, they are actually there in A, 2, 3, 5, 7. So here we can say that B is a subset of A. Alright, so here if we find out A intersection B, this will be equal to what? We have to consider only the elements which are common in both A and B. So both A and B, you see we have 2, 3, 5, 7 common to both A and B. So A intersection B will be 2, 3, 5, 7. Okay, and you see here 2, 3, 5, 7 is actually what? It is a set B. So if B is a subset of A, then A intersection B will be equal to B itself. Now, let us see the Venn diagram representation of intersection of two sets A and B. See, we have already discussed about the union of sets in our previous videos which will be available in the playlist. So here, let us see how to represent the intersection of two sets A and B using Venn diagram representation. So here you see, this is a universal set. Okay, this one is set A, this one is set B. Alright, now when we consider A intersection B, we have to choose elements which belong to both A and B. So here we have to choose elements which belong to both A and B. That is, this shaded portion actually indicates the intersection of A and B. That is, if you consider this part, this actually belongs to A only, not to B. If you consider this part, that belongs to B only, not to A. So we cannot consider those portions while we are considering the intersection of two sets. While we are considering intersection of two sets, we have to choose elements which belong to both A and B. So this shaded part, this shaded portion actually indicates the intersection of the two sets A and B. Now, let A is equal to 2, 4, 6, 8 and B it is a set of 1, 3, 5, 7. Here, if we find out A intersection B, okay, what will be A intersection B? We have to consider the elements which belong to both A and B, that is common in both A and B. So here you see we have 2 here in A but not in B, so we cannot consider that. 4 in A but not in B, 6 in A not in B, 8 in A not in B. So we cannot, similarly if you consider any elements in B, they are not present in A as well. So while we are considering A intersection B, we won't be getting any elements in this set. That is, we will be getting a null set or an empty set. So in such cases, here the two sets A and B, okay, here A and B are two sets such that A intersection B is equal to an empty set or phi or null set. So A and B, they are called as disjoint sets. Okay, disjoint sets. There are no elements common to both A and B. Alright, so here we have two sets A and B such that A intersection B is a null set, phi or an empty set. Then A and B are called as disjoint sets. Now, when we consider the Venn diagram representation of disjoint sets, you see this rectangle one is the universal set. We have set A here, we have set B here. See, when we consider disjoint sets, A intersection B must be a null set. That means there should not be any common points for A and B. That is, there should not be any common, portions, shared by both A and B. So, you see here A and B are drawn separately. Okay, because these two are disjoint sets. So, this is the Venn diagram representation of disjoint sets. Now, let us see some properties of operation of intersection. The first property is A intersection B is equal to B intersection A. And this is known as commutative law. That is, for example, you just consider A as set of 1, 2, 3 and B as set of elements 2, 3, 4 and C as set of elements 3, 4, 5. So here, if you find out A intersection B, this will be equal to what? You have to consider the elements which belong to both A and B. So here you see 2 is common in both A and B, 3 is common in both A and B. Okay, 1 is not common in both A and B, 4 is not common in both A and B. So when we consider A intersection B, it will have elements 2 and 3 only. Okay, similarly, you just consider or find out B intersection A. So here also, while we are considering B intersection A, we have to consider the elements which belong to both A and B. So here you see 2 and 3 are the only common elements for both B and A. So here the intersection B intersection A, that will also be the set 2, 3. So here you see A intersection B and B intersection A both are the same now. That is, A intersection B will be equal to B intersection A, and this is known as commutative law. Now, let us see the next property of intersection, that is A intersection B intersection C is equal to A intersection B intersection C, and this is called as associative law. So, let us consider the set A, B and C like this. Now, let us find out A intersection B, which we have already found out. A intersection B is equal to what? 2, 3. Okay, now what about A intersection B intersection C? So here we will be getting a new set which has elements belongs to both A intersection B set and C set. Okay, so you see in A intersection B we have 2, 3. In set C we have 3, 4, 5 elements. So the common elements belong to both A intersection B and C. They are actually 3 now, because in C we have 3 which is present in A intersection B. We have 4 not in A intersection B. We have 5 not in intersection, A intersection B. Similarly, here we have 2 which is not in C. So, the only elements which are common to both C and A intersection B is 3. Alright, so A intersection B intersection C is this set which has only one element, 3. Now, see, we have already, okay, now let us see what is B intersection C. B intersection C, so you see, this is set B and this is set C. We have to write the elements which belong to both, that is present common in both. So you see, 2 is only in B, not in C, so we cannot take 2. 3 is both in B and C, so you can write 3 here. And 4 is both B and in C, so you can take 4 here. And here we have 5 which is not in B. Okay, so this is B intersection C. Now what about A intersection B intersection C? So A intersection B intersection C. That is, we have to consider the common elements in A and B intersection C. In A we have 1, 2, 3. In B intersection C we have 3, 4. So you see 1 and 2 present only in A, not in B. Sorry, B intersection C. 3 is present in A as well as in B intersection C. So we can write 3 here. Similarly, here we have 4 which is not in A. So we cannot write 4 here. So this is the set A intersection B intersection C. Okay, now you compare these two. A intersection B intersection C is set 3 and A intersection B intersection C is actually set of 3. Set of an element which has, the set which has only one element 3. So both are the same now. That is A intersection B intersection C is equal to A intersection B intersection C, and this is known as associative law. Now let us consider the next property of operation of intersection, which is phi. Phi is the null set. Phi intersection A is equal to phi and U intersection A is equal to A, and this is actually called as law of phi and U, that is law of null set and universal set. That is, for example, let us consider the base set or the universal set as set of these elements 1, 2, 3, 4, 5, and set A is 1, 2, 3. Actually it has elements 1, 2, 3 in it. Okay, now if you find out phi, what about phi? Phi is a null set, no element will be there in the set. So if you consider phi intersection A, so you see, when we consider intersection, we have to consider the elements which belong to both phi and A. So A is 1, 2, 3, phi has no elements in it. So there won't be any common elements present in phi and A, no, because there are no elements in phi. So this will be again a null set, that is, this will be phi. Okay, similarly, what about U intersection A? This is U and this is set A. So U intersection A, we have to consider the elements which belong to both U and A, that is common in both U and A. So you see, here we have 1, here also 1, 2, 2, 3, 3. What about 4? It is only in U, not in A. 5 only in U, not in A. So we cannot consider those elements here while we are writing intersection. So U intersection A will be what? Set of 1, 2, 3. Alright, and you see this set is actually the set A now. So this is set A. So U intersection A will be equal to A itself, and phi intersection A will be equal to the null set phi. Next, let us see the idempotent law, that is A intersection A is equal to A. You see, A is 1, 2, 3, set 1, 2, 3. And again, if you are considering A, that is, you see, set A is set of these elements 1, 2, 3. Again, we are writing one more A, that is the same set 1, 2, 3. Now, what about A intersection A? We have to write the elements which are present in common in both, that is 1, 2, 3. Okay, so this is actually what A. So A intersection A is equal to A, and this is called as idempotent law. Now, let us consider the next one, that is A intersection B union C is equal to A intersection B union A intersection C. And this is actually called as distributive law, that is, intersection distributes over union U. That is, for example, let us consider the three sets A, B and C like this. Here, if you find out B union C, I am talking about the left hand side of this equation. So B union C. What about B union C? While we are writing B union C, see, we have already discussed about the union of two sets in our previous video. Please watch that. You will get an idea about how to take the union of two sets. So B union C, when we consider B union C, you have to write all the elements in, you see, in B and all the elements in C, but no need to repeat the elements. Right. So you see, in B we have 2, 3, 4. Then what about C? We have 3, 4, 5. 3 and 4, once we wrote it, so no need to write it again. Then what about 5? So this is B union C. Okay, now what about A intersection B union C? A intersection B union C. So while we are considering intersection of two sets, okay, we have to write the elements which are common in both. So in A we have these elements 1, 2, 3. In B union C we have 2, 3, 4, 5. So which are the common elements here? 2 is common in both. 3 is common in both. Okay, no other elements are common in both. So A intersection B union C will be the set of these two elements 2 and 3. Okay, now what about A intersection B? A intersection B. So here we have to write the common elements present in both A and B. So you see here we have 2 common in both, 3 common in both. 1 and 4 are not common. So this is 2, 3. Okay, now what about A intersection C? A intersection C. A intersection C. So A intersection C, that is you see in A we have 1, 2, 3 and in set C we have these elements 3, 4, 5. So while we are considering A intersection C, we just want to write the common elements, that is the elements which belong to both A and C. So you see the only element belongs to both A and C is 3. Okay, so A intersection C will be set of this element 3. Alright, now what about this right hand side, that is A intersection B union A intersection C. But what about this? You see in A intersection B we have these elements 2 and 3. A intersection C we have set of this element 3. So while we are considering the union of these two sets, we have to write all the elements in set A intersection B and in set A intersection C, but no need to no need to repeat the elements. So here you see in A intersection B we have 2, 3. In A intersection C we have 3, which has already written here, so no need to write it again. So this is A intersection B union A intersection C. So you see the left hand side A intersection B union C, that is set of 2 and 3. Now the right hand side A intersection B union A intersection C, and that is also you see the set of 2 and 3. So you see these two are the same now. So we can write A intersection B union C, that is equal to A intersection B union A intersection C, and which is known as distributive law. That is this intersection distributes over union. Okay, now you see we said A intersection B union C, that can be written as A intersection B union A intersection C, which is known as distributive law. And you see from the Venn diagrams we can explain this law. That is, here you see this rectangle one, that is a universal set, and here I have considered the 3 sets. Okay, one is set A, set B and set C. So if we consider this B union C, so when we consider B union C, when we consider union, we have to consider all the elements in B as well as in C. So you have to shade all the portions of B and all the portions of C. So you see this shaded portion actually represents B union C. Okay, now if we take A intersection B union C. So you see in B union C we have all the parts of B and all the parts of C. Then now we consider A intersection B union C. That means we just want to consider the common portions of A and B union C. Okay, so you see in B union C we have these portions, this one and this one, which is common for A as well. So when we consider A intersection B union C, that will be this shaded part, okay, which is common for both B union C and A. Now if we consider A intersection B, so while we consider A intersection B, we just want to shade the common parts, common areas of A and B. So you see A and B shares this particular common region, no? So this actually represents A intersection B. Now if we consider A intersection C, we want to consider the common portions shared by A and C. So you see A and C shares this common portion. Okay, now if we consider A intersection B union A intersection C, that is we have to consider the common portions of A intersection B and A intersection C. So you see A intersection B has this shaded portion and A intersection C has this shaded portion. Now when we consider not the common portions, you see, while we consider A intersection B union A intersection C, we can consider all the portions shared in A intersection B and A intersection C. So you see in A intersection C we have this portions shared, and in A intersection C we have this portions too shared. So when we consider A intersection B union A intersection C, this looks like this. Now you see A intersection B union C is this, and A intersection B union A intersection C is this. Now you just compare these two. Both are the same, no? Okay, so we can say that A intersection B union C, that will be equal to A intersection B union A intersection C. So in this video, we have discussed about the intersection of sets. I hope it is clear to you. Thank you.